Today we are starting our first part of our chemical calculations section. We are looking at how to calculate molar mass. Because I'm not 100% confident everybody knows how to count atoms, that's actually going to take a step back just to make certain that everybody knows how to count atoms. So, remember we've seen this before where our subscript tells us our number of atoms. So if I'm looking at something like water, that 2 is telling me that I've got 2 hydrogens, and the lack of a number is telling me that I've got one of those numbers. So in water, I've got 2 hydrogens, 1 oxygen. In copper 2 sulfate, I've got 1 copper, 1 sulfur, 4 oxygens. In my sodium bicarbonate, I've got 1 sodium, 1 hydrogen, 1 carbon, 1 oxygen. Those are fairly straightforward because they tell you exactly how many atoms they are. The only time it gets a little complicated is when you're dealing with polyatomics with your parentheses. So the thing you want to pay special attention to is these numbers that are outside the parentheses. Whenever you see numbers outside the parentheses, they multiply everything that is inside the parentheses. And they only affect the stuff that is inside the parentheses. So this 2 outside that nitrate is going to affect the 3 beside the oxygen and the 1 beside the nitrogen. So once we go and count our number of atoms, we've got copper having 1 copper, 2 nitrogens, and 6 oxygens. It doesn't matter how many polyatomics there are, the number outside the parentheses multiplies everything inside the parentheses. So if we're looking at ammonium phosphate, we've got 3 nitrogens, 3 times 4, 12 hydrogens, 1 phosphorus, and 4 oxygens. So I find some students find it very useful to kind of have that little arrow to remind them that they need to multiply in. Now, said this lesson is about molar mass, though. Molar mass is the sum of atomic masses. Remember, atomic mass is a thing that's below the symbol on the periodic table. When we're looking at calculating the molar mass, we have to take into account the number of atoms of each element. So if I look at my example, calcium phosphate, we have a total of 3 calciums, 2 phosphoruses, and 8 oxygens. Now, yes, I could add calcium 3 times, 40.08 plus 40.08 plus 40.88. Gets a little repetitive. So instead of adding it 3 times, what I'm actually going to do is I'm going to take my number of atoms times its atomic mass. And then I'm going to add to it the next element, its number of atoms times its atomic mass. And I'm going to add the next element. Now, when you are finding your molar masses, don't round them to a whole number. Keep all the numbers that you see on your periodic table. Add them all up because, yes, we are looking at the sum of atomic masses. Now, 2 different ways to show the same thing. Gotta love calculator. Here we go. One would be just kind of in a straight line linearly. One would be like I'm showing it on the screen with them on top of each other. Either way, you're looking at total number of atoms times each of their atomic masses. So either way you show it, you get to the same answer. We have a molar mass of 310.18 grams. What that means is if I had 1 mole of this substance, it would weigh exactly 310.18 grams. Remember, a mole is the unit of measurement that is unique to chemistry. It tells me how much of a substance we have. Now, when you're looking at calculating your molar masses, our number of atoms doesn't really affect how you round. We're looking at that actual mass. So if my mass has 2 numbers after the decimal, my average atomic mass is going to have 2 numbers after a decimal. My mass has 3, we're going to round it to 3. Now, you've got to know your nomenclature rules in order to do molar mass, because this builds on top of previous skills. So do remember that when we are looking at our names, anything that ends in a TE, whether it be an ATE or an IT, is a polyatomic. And that means it's probably also an ionic compound, which means we have to balance our number of atoms, balance our charges before we count our number of atoms. So let's say I'm looking at something like aluminum sulfate. I don't know why I put a parentheses there. I know that aluminum has a charge of 3, sulfate has a charge of 2. My charges can't reduce, they don't balance out, so we just swap and drop. I've got 2 aluminums and 3 sulfates, but I'm not going to find the mass for sulfate on my periodic table. I have to look at the individual mass of each element. So when I go to find its molar mass, I've got 2 aluminums, each weighing 26.98, plus, remember, that number multiplies everything inside. So 3 sulfurs, each at 32.07, plus my 12 oxygens. And since I'm just making this up off the cuff, I don't know the mass off the top of my head. So handy dandy calculator. Guys, if you're using your phone as a calculator, I would possibly recommend multiplying, then adding up, or switching to Desmos if you don't have an actual handheld calculator. My Casio and my TI both would actually do the math properly. If you have just a dollar store calculator, it may not. So handy dandy calculator tells me that my molar mass of aluminum sulfate is 342.17 grams, which is just a fancy way of saying that if I had 1 mole of that substance, it'd be 342.17. So pause the video, see if you can calculate the molar mass of each of these 2 substances, then come back and see if you got it right. Hopefully you've noticed that we've got more ionic compounds than we do anything else. And do remember that with ionics and acids, you do have to balance your charges before you get the final chemical formula. Once you have that final chemical formula, don't change the subscripts. Those subscripts stay exactly as they are. So barium sulfate, look at the periodic table. Barium is a +2. My cheat sheet, this ends in a T, tells me I'm looking at my polyatomics. SO4 -2 is sulfate. Well, these charges balance out. So I can reduce and swap and drop. I can just write the letters because they balance each other out. Either way, I get my chemical formula of BaSO4. It's the lowest ratio of atoms that make each other stable. So to find its molar mass, I add up 1 barium, 1 sulfur, 4 oxygens. Remember, if there's not a number here, it's an invisible 1. If you need to write that 1, you are more than welcome to. So this is one way to show the calculation for barium sulfate. It's not the only way, but no matter how you do it, using our current periodic table, you should get 233.40 grams. So vanadium VI sulfite. VI, remember, is our Roman number 6, and it tells me that my vanadium has a charge of 6. My sulfite, SO3, because it ends in a TE, -2. Remember, if it was a single element, it would be sulfide, not ite or 8. So those 2 exponents are both reducible. They are even numbers, which means I can divide both of them by 2 so that I can get the lowest ratio of atoms, and then I swap and drop. Once I swap and drop, I get 1 vanadium and 3 sulfites. To find the molar mass, I add up each of these individual atomic masses. So 1 vanadium, 3 sulfurs, and 9 oxygens. And my molar mass for vanadium is 291.5. Oh, bad misrange. You forgot your unit. Grams, because mass is measured in grams. That is how you find molar mass. Second part of the video lesson will be added shortly. So the thing about percent composition is it gives you the relative amount of each element in a compound. It could be useful in predicting how much of a product you're going to make or what percent of the compound is going to turn in this particular substance. It is calculated by finding the total mass of the element and divided it by the total mass of the compound. Now, my total mass of my element does include each individual number of atoms. Now, the nice thing about percent composition is if you happen to find the percent composition of all of the elements, you are able to add them all up and you should get something that is really, 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 really close to 100, if not exactly equal to 100. Now, due to rounding, sometimes you're going to get something that's slightly off, give or take 0.02%, just a smidgen. But our percent composition is the mass of the element over the mass of the compound. Gotta love spelling errors, but whatever. Now, the thing about our mass of our element is we do have to take into account the total number of atoms. Total number of atoms. So, if I'm looking at something like water, my H2O, I have to take into account the fact that I've got two hydrogens, each of a mass of 1.01, over my total molar mass of 18.02. So mass of compound is also known as molar mass. Either one of these terms are interchangeable. Two different ways to think about the same thing. Take the method that makes the most sense to you and go from there. Now, the thing about finding percent is you also have to remember to multiply by 100 because we are getting the percent that it contains. So if I look at water, hydrogen makes up 11.2%. Hydrogen makes up 11.2% hydrogen. And that means if I were to do the exact same calculation for oxygen, I would look at one oxygen atom times its molar mass, which is 16, over the molar mass of water. My grams end up canceling out, multiply by 100. Oops, hit the wrong button on the calculator. And the percent composition of oxygen in water is 88.79% oxygen. Now, when you're writing your percent compositions, round to the same number of numbers as in your atomic mass. So for most of our atomic masses, it's going to be 3 or 4 numbers. There are only, a couple of exceptions. Your larger atomic masses, of course, get into 5 digits, 3 for the hundreds, and then your decimal places. Oh, I just did that one. Now, as I said, you can have a built-in self-check feature if you find the percent composition of each element in the compound. You add them all up, and they should equal really, 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 really close to 100%. One additional decimal place. If I didn't, it would equal 99.99, which is really, really close to 100. So because we are rounding, you might get something slightly simple, slightly different. So let's find the percent composition of each element in calcium phosphate. Calcium phosphate. So remember, you need the mass of the compound. This is my mass of my compound. It will not be given to you. You have to calculate it. We found it by adding up 3 calciums, 2 phosphoruses, and 8 oxygens. Now we're going to find the percent composition of each element. So the total number of atoms of that element times its atomic mass divided by this molar mass will give me my mass of my compound. Oh, I actually did it separate when I typed it up. I found the total mass of calcium, but normally what I would do is 3 atoms of calcium times 40.08 divided by 3 to 10.18 times 100. Number of atoms, my atomic mass, and my molar mass, all times 100. Doesn't matter which way you do the calculation, you're going to still get to the same basic answer. So if I were to look at it for my phosphorus, 2 phosphorus atoms times its atomic mass divided by the mass of the compound times 100. And last but not least, my oxygen, 8 oxygens times 16 divided by 310.18 times 100. Yes, I know it seems a little redundant to write that same calculation over and over again, but we're actually showing where our numbers are coming from. And as we will see further we get into this course with chemistry, not only is it important to show where the numbers are coming from, but it's also important to show where your units are coming from. So self-check feature, if I were to add up all of these atomic masses, I should get something that is really, really close to 100%. So I actually happen to get exactly 100. Don't freak out if you don't get exactly 100%. That is finding percent composition, which was the second part of today's lesson. Hope you enjoyed, and just remember that I am in the Google Meets if you need me.